You know, tucked away deep inside your head is one of the most incredible pieces of biological machinery you can possibly imagine. I know I'm not talking about your brain. Well, not just your brain. It's your inner ear. It's this microscopic marvel that translates the physical world of motion and vibration into the rich tapestry of sound and balance that literally creates your reality. So let's dive in and see how this thing actually works.
I mean, that sounds impossible, right? The lurching feeling in your stomach as you plunge down a roller coaster seems like a world away from the delicate, faint sound of a pin dropping. They feel like completely separate senses. But what if I told you they weren't? That they both start in the exact same place with the exact same microscopic sensor. It's a biological miracle that turns the physical world into the language of the brain.
And here it is. This is the hero of our entire story, the hair cell. Now, it's not actually hair, of course, but this little guy is the fundamental building block for both our sense of hearing and our sense of balance. Seriously, everything we're about to explore, from listening to your favorite music to just standing upright, it all starts with this one incredible cell. And here's a closer look. Just look at that elegant, almost pipe organ-like arrangement of the stereocilia. These are the hairs that give the cell its name, and their sensitivity is it's almost impossible to wrap your head around. The slightest physical nudge to this bundle, and I mean we are talking about movements on the scale of atoms, is all it takes to kickstart the entire process of perception. It's absolutely exquisite. Now, the magic that this hair cell performs has a name: mechanotransduction. It sounds a little technical, but it's a really simple concept for a totally profound process. It's all about turning a physical push or a pull into an electrical signal. And that electrical signal is the universal language of the nervous system. The hair cell is just one of its most elegant translators. So how does it do it? Well, it's this beautiful, super fast, four-step chain reaction. First, some kind of force, either from a sound wave or your head moving, bends that bundle of cilia. Second, as they bend, tiny little molecular ropes called tip links that connect them get stretched. This yanks open these tiny little gates or ion channels. Third, potassium ions, which are all over the place in the surrounding fluid, just flood into the cell, changing its electrical charge. And finally, that change in voltage is the trigger. It tells the cell to release chemical messengers to a neuron, which then fires off a signal to the brain. It's just bend, pull, rush, send. That's it. Incredibly elegant. Okay, so we've got this amazing little sensor. Now let's see what our body builds with it. And we're going to start, maybe surprisingly, not with hearing, but with balance. This is your vestibular system. It is your personal biological gyroscope and accelerometer. Just think about that for a second. You have a high-tech physics engine running 24/7 inside your head just to tell your brain where you are in 3D space. And here's the system's layout. You can see two main parts here. You've got those looping semicircular canals, and then the more central bits, the otolith organs. Now, notice how they're all arranged at right angles to each other, what we call orthogonally. That is not an accident. That is the entire key to sensing motion in all three dimensions. So these three semicircular canals, they act as your gyroscope. Each one is filled with fluid. When you turn your head, like say you shake your head no, the fluid in that horizontal canal kind of lags behind because of inertia. This lagging fluid pushes on this little gelatinous blob, which bends the hair cells inside it and sends a signal to your brain saying, hey, we are turning left. And because you have three canals covering all the axes of rotation, your brain gets a perfect real-time readout of any way your head is turning. Okay, so what about the other kind of motion? Well, that's where the otolith organs, the utricle and the saccule, come in. These are your accelerometers. They detect straight line or linear acceleration, like when you hit the gas in a car or go up in an elevator. Inside these organs, you have these tiny calcium crystals. They're basically microscopic rocks sitting on top of a gel that's full of hair cells. When you accelerate forward, those little rocks lag behind, shearing the gel and bending the hair cells. And get this, they also detect the constant pull of gravity, which is how you know which way is down, even if your eyes are closed. All right, so that's balance. But that exact same hair cell, with just a few clever tweaks to the system around it, also powers our entire sense of hearing. So now we're going to move into the cochlea, which you can think of as a kind of biological prism, not for light, but for sound. What you're looking at here is the fundamental principle of hearing. See, any complex sound, my voice, a piece of music, a car engine, is actually a mix of many simple, pure frequencies all jumbled together.
The cochlea's job is to do something that takes engineers complex math and powerful computers to do, a Fourier transform. It physically deconstructs that complex sound wave and splits it apart into all of its individual ingredients, all its frequency components, from low to high.
So how on earth does it do that? Well, this image shows the cochlea as if we've unrolled it. And inside is this long sheet of tissue called the basilar membrane. The crucial bit here is that its physical properties change along its length. The base, right at the start, is narrow and stiff, so it vibrates like crazy in response to high-frequency sounds. But the apex at the far end is wide and floppy, so it only vibrates in response to low-frequency sounds. So a sound's pitch is encoded simply by where on this membrane the vibration is strongest. It's pure physics.
And what's amazing is that this spatial map for frequency, it's called tonotopic, is meticulously preserved. Neurons that are connected to that high-frequency base of the cochlea, they travel to one specific spot in the brain, and neurons from the low-frequency apex go to another. It is literally like a piano keyboard has been laid out across your auditory cortex, with each key in your brain corresponding to a very specific spot in your ear.
Okay, so we know what we're hearing based on which hair cells are vibrating, but how do we know where a sound is coming from? Well, your brain acts like a brilliant detective, using these tiny, tiny clues in timing and loudness to build a complete 3D map of the world around you, just from sound. So the brain basically uses two main tricks, and it depends on the pitch of the sound. For low-frequency sounds, which have these really long wavelengths that can just wrap right around your head, it relies on timing. It calculates something called the interaural time difference, which is just the microscopic delay between a sound hitting one ear versus the other. But for high-frequency sounds, which get blocked by your head, it uses loudness. It calculates the interaural level difference created by your head's acoustic shadow. And your brain actually has dedicated hardware for each of these jobs located way down in the brainstem. As you can see here, a little cluster of neurons called the medial superior olive, or MSO, is built to handle the timing differences. And a different one, the lateral superior olive, or LSO, handles the loudness differences. These circuits are computing your soundscape in real time, way before you're ever consciously aware of it. The way the MSO works is it's brilliant. It contains neurons that are wired to get signals from both ears, but the nerve fibers leading to them have different lengths. So a specific neuron will only fire its signal when the electrical spikes from the left and right ears arrive at the exact same moment. This means a sound from the left has to travel a longer neural path to hit the same coincidence detector as a signal from the right ear. It's a clever way to turn a time difference into a location map in the brain. Now, the LSO's strategy is a little different. It's more like a tug of war. Neurons here get an excitatory, or go, signal from the ear on the same side, but they get an inhibitory, or stop, signal from the ear on the opposite side. So the neuron's firing rate is basically just the result of that subtraction. If the sound is louder on the left, the go signal from the left wins and the neuron fires like crazy. If it's louder on the right, the stop signal wins and the neuron goes quiet. It's simple, but incredibly effective. Okay, so to wrap this all up, let's look at what happens when evolution takes these same basic principles we've been talking about and just pushes them to their absolute mind-bending limit. Let's talk about bat echolocation. Bats have evolved something that is truly remarkable. It's called an acoustic fovea. You know how the fovea in our eye gives us a tiny spot of ultra-high-resolution vision? Well, a bat's cochlea has a massively overrepresented section that is tuned to a very, very specific and narrow slice of frequencies. This lets them detect tiny, tiny changes in sound that would be completely invisible to us. And with this specialized hardware, bats assemble an incredible sonar toolkit. They use what are called frequency-modulated sweeps. Think of a fast descending chirp to figure out a target's distance based on the echo's delay. Then they use constant frequency tones to measure a target's speed using the Doppler shift. You know, that's the same thing that makes a siren change pitch as it drives past you. And finally, they use that acoustic fovea to get an unbelievably high-resolution reading of the tiny Doppler shifts caused by something as small as the fluttering wings of a moth. They aren't just hearing, they are literally seeing their world with sound. So, from the simple bend of a single type of cell, our brain constructs our entire sense of motion and our entire world of sound. It's a powerful reminder that what we perceive as reality is just one interpretation, a model built by our specific biological tools. And it kind of leaves you wondering, doesn't it? What other realities are out there being perceived by creatures with entirely different senses, decoding the universe in ways we can only dream of?